In this work, we propose two guidance methods for navigation using the Earth's magnetic field. These guidance methods are designed to increase navigation accuracy by leveraging regions where magnetic data is rich. Why should we consider magnetic field-based navigation? Well, when GPS is not reliable or is not available, alternatives for global navigation are needed. The most common navigation alternatives use a feature-based LiDAR or visual aided system. However, approaches with these sensors might struggle in uniform scenes. Also, they depend on weather and lighting conditions and become more challenging for visually dynamic scenarios. On the other hand, magnetic field based navigation does not depend on the weather or lighting and is available globally and is nearly unjammable because magnetic interferences decay at a rate of r cubed. More specifically, in this work, we're referring to magnetic field anomalies when we talk about magnetic field. This anomaly field is also called the Earth's crustal field. And in contrast with the concept of the Earth's core field, magnetic anomalies are static over geological timescales, and differences in magnetic field intensities can be more significant as well. The image on the left is a magnetic anomaly map, and it is available online. Now, what is the idea behind magnetic navigation? Well, provided that some agent is equipped with a magnetometer and that we have a preloaded map, the idea is the following. We use the agent's dynamic model to compute its estimated position, and when available, we obtain a magnetic field measurement. Then, the received measurement is compared with our estimated measurement, which is obtained by querying the map at the estimated location. By comparing the sensor reading and our estimated measurement, we can establish a measurement residual that a navigation filter can use to perform a state update. In this work, we use a standard particle filter to process the magnetometer measurements. When navigating from one location to another, the accuracy will depend on the anomalies available along the path taken. But what if we intentionally plan the agent's path to gain more information? That is, how can we reach our destination while exploiting rich information regions? This concept is pictured on the right plot. Here, the yellow path is an information-aware planner that primarily focuses on information gain. The white path is the straight line path that simply navigates to the goal without attempting to increase information gain. The path in the middle balances information gain and total distance to the goal position. In this work, we show that magnetic navigation accuracy can be improved when information-aware guidance methods are used. We propose two methods. The first one is based on maximizing the determinant of the system observability gradient, and the second on maximizing the entropy reduction of the system. Both methods aim to increase the information gain along the travel path. However, the gradient method is only based on the point estimate of the system state, while the entropy technique considers the distribution of the state. Both methods are tested on a ground robot that navigates using an indoor magnetic map. The optimization problem is solved via standard dynamic programming with a receding horizon p steps ahead of the agent's location. The decision variable is the angular rate of the ground robot. In this video, the observability approach is running online. It's guiding the robot to the coordinate marked with the red X. In this run, the optimization problem is solved with a receding horizon of 5 steps ahead. And overall, one can see that the magnetic field gradients attract the planned path and that the uncertainty ellipse is reduced the most in these regions as expected. In general, the experiments revealed that the information-aware approaches remain near straight paths, However, as shown in this plot, the reduction of the uncertainty presented here as the trace of the estimated covariance was up to 300% over some regions. The bar plot shows the average covariance trace for different weight ratios used in the optimized cost function to penalize distance to goal and information gain. Here, the yellow bar represents the run with no information optimization, and the blue bars are runs with information optimization. Overall, it is seen that there is a significant advantage of using the observability aware guidance method. Similarly, the entropy approach shows a gain in accuracy, and depending on the local gradients, it was seen to reduce the navigation uncertainty by up to 200%. While it is true that the information gain depends on the map content, it might be better to leverage rich regions, especially for long missions where it might be desired to bound the navigation uncertainty. Magnetic anomaly based navigation is promising, but there are still some challenges. One of the current lines of research is on-chip calibration, which consists of removing the agent and onboard system effects from magnetic measurements. Like in this example, where the control surfaces of an airplane make the measured magnetic field fluctuate. The calibration approach should then remove the control surface effects from the measurement quantity and recover the corrected value as shown in the right figure. At this point, I'm open to questions.